Good morning, children. Welcome to online class. Today we are going to discuss superposition principle. In the last class we see about Coulombs law. Coulombs law explains the interaction between 2 point charges. If there are more than 2 charges, the force on one charge due to all the other charges need to be calculated. If there are more than 2 charges, the force on one charge due to all the other charges need to be calculated. So for this, Coulombs law we can't able to apply. So we have come to the new concept, that is the superposition principle. The superposition principle explains the interaction between multiple charges. According to this superposition principle, the total force acting on a given charge is equal to the vector sum of forces extracted on it. Vector sum of forces extracted on it by all the other charges. So this is the statement of superposition principle. The total force acting on a given charge is equal to the vector sum of forces extracted on it by all the other charges. So we can calculate this concept. For that, let us consider a system of n charges. Here I am taken Q1 is the first charge and Q2, then Q3, then Q4, Q5, etc. The last charge I am going to take as for Qn. Now I want to calculate what is the force extracted on the charge Q1 by all other charges. So first step I am going to calculate the force on Q1 extracted by the charge Q2. Okay, the force on Q1 extracted by the charge Q2. How we can write the formula? The force on Q1. So I can write the force on Q1 by the charge Q2. So F12 vector is equal to, what we will get? K into, okay, what are the two charges here? Q1 and Q2. Q1 and Q2 divided by, and here see the direction. What is the direction here? 2 to, direction is from 2 to 1. Okay, the direction is from 2 to 1. So I can write here, the direction is listen, R21 square into R21 cap. Understand, children? Like this only we are calculating the formula for the first. Okay, second step we are going to calculate the F13 vector. For F13 vector, listen, we have taken the charges Q1 and Q3. Okay, so for understanding purpose, listen, this is the Q3 and this is I am taken as what? Q1. Okay, so the force extracted on the charge Q1. So F1 by Q3. So F13 vector, that is equal to K into Q1, Q3. These are the two charges, Q1, Q3 by, what is the direction the force extracted? That is 3 to 1. So I can write here K Q1, Q3 divided by R31 square into R31 cap. Like this, we can calculate for n charges. By continuing this, the total force acting on the charge Q1 due to all other charges we can written as F1 vector total. Okay, we are going to calculate for total force. So F1 is the force extracted, that is by the all the charges on Q1. force extracted by all the charges on Q1. So F1 vector total is equal to F12 vector plus F13 vector plus F14 vector plus etc. Last one F1n vector. So if you see the first equation, what is common? K. So we can write K as common, then write the remaining all the values. For the first one, Q1, Q2, second one, Q1, Q3, third one, Q1, Q4, and the last one, Q1, Qn. In the denominator, listen, 2 to 1, 3 to 1, 4 to 1, n to 1. So correspondingly, we can write the formula also. K is taken as common. Then Q1, Q2 divided by R2 square, that is R21 square into R21 cap plus Q1, Q3 divided by R31 square, R31 cap plus Q1, Q4 divided by R41 square, R41 cap plus etc. Q1, Qn divided by Rn1 square into Rn1 cap. Okay, understand children? So this is only we are called as what? Superposition principle. Next topic, electric field. So before come to the concept of electric field, the interaction between two charges is determined by Coulombs law. Here we having one question. How does the interaction itself occur? Let us consider a point charge Q is kept at a point. For example, I am saying consider, listen, it is kept at a point O in phase. If another point charge is placed at some distance, okay, at some distance, that point is I am going to take as what? P. Here I am placing another one charge Q0 from the first point charge. It experiences either an attractive force or repulsive force. This is called an action at a distance. This is called as what? Action at a distance. But how does the second charge know about the existence of the first charge which is located at some distance away from it? To answer this question, Michael Faraday introduced the concept of field. According to him, every charge in universe creates an electric field in the surrounding phase. And if another charge is brought into its field, it will interact with the electric field at that point and will experience a force. This way, interaction will be taken place. The same concept only already you studied in the 11th standard in unit 6 in the concept of what? Gravitational field. Here, both the electric and gravitational force are non-contact force. Hence, the field concept is required to explain action at a distance. So, again for understanding, let us consider a point source. That is, listen, here I am going to take on one point charge Q. Let us take one point charge Q at one particular point. For example, I am taken, this point is taken as what? O. Okay, at the point O, I am taken one source point charge Q. Then another one point charge Q0. Actually, this Q0 is nothing called as what? Test charge. The Q0 is taken as what? Test charge. The test charge always we are taken as what? Positive. Remember, everywhere listen. The test charges we are taken as what? Unit positive charge. Listen, initially we having one charge, that is what? Q. At a distance, we are taken another one charge Q0. Here the distance is taken as what? R, at a distance R from the charge Q. Now, according to Coulombs law, we can write the formula F is equal to K. We know that there is a constant term K. The first charge is Q and the second charge is Q naught, and these are separated by the distance what? R square. This is the magnitude. If I write this equation in terms of vector, if I write means listen, I will get F vector is equal to K Q naught by R square into R cap. Okay, understand children? So, if I substitute the value of K, what is the value of K? That is 1 by 4 pi epsilon naught. So, I will get here the formula 1 by 4 pi epsilon naught Q naught by R square into R cap. Okay, understand? Just we get the force, there is electrostatic force experienced by the charge Q naught due to the charge Q. The charge Q creates an electric field in the surrounding space. With this effect, we can feel that another charge. It is measured in terms of quantity, that is only we are called as what? Electric field intensity or electric field. Okay, that is measured in terms of what? Electric field intensity or electric field. So, there is very important 2 mark question. Define electric field. So, define electric field, it is a very important 2 mark. So, the electric field at the point P at a distance R from the point charge Q. Listen once again. The electric field at the point P at a distance R from the point charge Q is defined as the force experienced by, okay, defined as the force that would be experienced by a unit positive charge. Okay, already I told that the test charge is taken as what? Unit positive charge. Okay, so only here given as unit positive charge placed at that point P. Okay, so the electric field at a point P at a distance R from the point charge Q. Okay, so once again we can draw the diagram. Here I am taken the source charge Q. Here we have taken the point P, that is the test charge Q naught. These are separated by the distance R. So at the point P, listen, the electric field at the point P I want to calculate. So the electric field at the point P at a distance R. Okay, at a distance R from the point charge Q. Okay, from the point charge Q is defined as the force that would be experienced. That is, the electric field is equal to, okay, the electric field at the point P at a distance R from the point charge Q is defined as the force experienced by a, or the force that would be experienced by a unit positive charge. What is the charge here? Q naught. Okay, already this test charges we are already I told that what? The test charge is what? Unit positive charge placed at that point P. So we will get the formula E is equal to F by Q naught. In terms of vector, E vector is equal to F vector divided by Q naught. Okay, so it is a very important 2 mark question. So we will get E vector is equal to F vector divided by Q naught, that is equal to KQ. Listen, we are considering what is the formula of F. F is equal to this formula, correct? That is 1 by 4 pi epsilon naught Q naught by R square into R cap. Here what is the concept here? Instead of listen Q naught, in the denominator Q naught, numerator Q naught will be cancelled. So we will get the formula that is equal to KQ by R square into R cap. Or if you substitute the value of K, we are getting the formula 1 by 4 pi epsilon naught Q by R square into R cap. Here R cap is the unit vector pointing from Q to the point of intercept P. Okay, this the direction is from Q to the point of intercept P. Okay, so listen here, we are written as what? The electric field is a vector quantity. Okay, so the SI unit, okay, it is a vector quantity. So the SI unit is Newton per Coulomb. The unit of the force is Newton, unit of the charge is Coulomb. So we are getting the unit, the SI unit is Newton per Coulomb. Okay, understand children? So next we are going to see the important aspects of electric field. The first point, if the charge Q is positive, listen, if the charge Q is positive, if I taken the charge Q is positive, then the electric field away from the source charge. Okay, so if I taken one, listen, if I taken here one charge plus Q, now I am taken one point P. At this point P, if you see the direction of the electric field is outward if the charge we are taken as what? Positive. Otherwise, if you take the charge is negative, the direction of the electric field is inward. Okay, it is very, very important. Okay, so we can say in the another way also. Listen children, at the point P, if you are placing the test charge. So here is also what? Positive charge. Test charge already I told you it is what? Positive. So positive, what happened? Repulsion. So only this the electric field is in an outward direction. Okay, now here I am taken here the second case, listen here, negative charge. Here the test charges we are taken as what? Positive. Negative, positive. What happened? Attraction. So only the electric field is towards the charge. Okay, so it is a very, very important concept. If the charge Q is positive, then the electric field point away from the charge. If the Q is negative, the electric field point towards the charge Q. Okay, understand? That is the first point. The second point you are going to see. Second point, if Q is positive, the force on the test charge Q0 is directed away from Q. That is already you know that lesson, that is the direction is like that. So we can calculate the force here. Okay, so listen, we know the formula E is equal to F by Q0. That is E vector is equal to F vector divided by Q0 in terms of vector. So if I want to calculate the value of force, cross multiply. What you will get? F vector is equal to Q0 into E vector. If the electric field at the point P, I am going to consider one test charge Q0. Then the force experienced by the test charge Q0 at the point P is F vector is equal to Q0 into E vector. Here, if the charge Q is positive, the force on the test charge Q0 is directed away from the charge. Okay, understand? Second lesson, if you are taken what? The Q is negative. Second case lesson, if you are taken the charge Q is negative. Negative means already you know that lesson. The force on the test charge Q0 is directed towards the negative charge. Okay, so here again listen, positive outward, negative towards. Okay, the same concept here, electric field also outward, force also outward. Here, force also, electric field also towards, force also towards. Okay, that is the second point. Next come to the third point. In third point, listen, we are going to see about the electric field is independent of the test charge Q0. Okay, and it depends only on the source charge Q. That means, listen, if I am taken the source charge that is positive, then depends upon that, listen, the direction will be taken place. If I take the charge is negative, with respect to that only the direction will be taken place. Okay, so the test charge is independent concept. So the electric field is independent of the test charge. It is very important, 1 mark also. And it depends only on the charge Q. Fourth point, electric field is a vector quantity. At every point in space, this field has unique direction and magnitude. If you see the diagram, here we consider one positive charge, one negative charge. Around this positive charge, we consider the 3 points P, Q and R. We know that the electric field formula E is equal to Q by 4 pi epsilon naught into R square. From this equation, when the distance increases, the electric field value will be decreases. If you see this diagram, the point P, Q, R. Okay, P, Q, R, if you see the distance, the P is a very short distance. So, the strength or magnitude of the electric field at the point P is stronger because the distance is lesser. P is stronger than at the point Q and R because the point P is closer to the charge. The point P is closer to the charge. Understand? Fifth point, test charge is made sufficiently small such that it will not modify the electric field of the source charge. In the definition of the electric field, it is assumed that the test charge Q naught is taken sufficiently very small so that if you are bringing the test charge, it will not move the source charge. So it is a very important point. Okay, understand children, if you are bringing the test charge also, it does not affect the main charge. Sixth point, you studied the formula E is equal to Q by 4 pi epsilon naught R square is valid only for the point charge. For continuous and finite size charge distribution, the integral technique will be taken place. However, this expression can be used as an finite sized charge if the test charge is very far away from the finite sized source charge. The same way only we studied in the 11th standard. Earth is very large, but we are taken that is also what? Point mass. Now there are two kinds of electric field. One is uniform electric field, another one is non-uniform electric field. Uniform electric field will have same direction. If you see, listen, the uniform electric field have the same direction and a constant magnitude at all the point in the phase. If you see, the non-uniform electric field will have different direction, different magnitude, or both are at a different point in phase. Okay, both are at a different points in the phase. The electric field created by a point charge is basically non-uniform. The electric field created by a point charge is basically non-uniform electric field. This non-uniform arises both in direction as well as magnitude. If you see here, the direction being radially outward or inward. The magnitude also changes as the distance increases. Okay, so there are two types. One is the uniform and another one is the non-uniform electric field. Understand?